Yeah, I'm almost there. You're feeling
Yeah, everyone who is sick is joining on Zoom. I have a couple of things which I wanted to talk about before we start. So first of all, I'm out of town, so I have to to go to Boston to MIT actually on Thursday, my flight. So I cannot do the office hours Thursday. And last week I couldn't do it because I was just busy and I even forgot to tell you. But can we do it on maybe Tuesday? I mean, I'll try to assign the homework today, but Tuesday, like same time on Tuesday. But I have some, I think I have a meeting, but 12. Is the homework due before or after?
the second class that expects me to do work.
But yeah, we can negotiate, we can push it further. My meeting tomorrow ends at 5. So yeah, so 5 tomorrow, then I'll send an announcement. I apologize for that. But it's just very hard to do Thursday this week. And then the second thing I wanted to ask, so I promised to answer a question last time, and I don't remember what we were talking about. You were asking what?
I remember I asked that question towards the end, but I don't remember.
It was something about zones and PCI drivers and everything. And we were looking at this figure, right?
All right. It's like the DMA zones should be core specific since PCIe controllers. Sorry, CPU specific since the PCIe controller.
Okay, so like last time we were talking about like kind of full-featured memory allocator and everything, and at the end I started saying, okay, Linux actually tracks in a non-uniform memory system like this one. Linux will track location of those like physical, like actual DRAM banks, and it says, okay, that will be zone 1, for example, right? And this will be zone 2, right? Hold on, node 1 and node 2, right? And inside those, and it will have a list of those nodes, right? And roughly speaking, each of these will like have its own page, like this array, which I was discussing, the metadata array. And then I said, okay, but actually Linux is even more sophisticated. And I mean, if you really build a system which need those properties, then you will have to pay attention. And the idea was that like a very good bit machine, 64-bit machines, you may run into some legacy physical devices, like for example, devices which cannot address beyond the 32-bit address range, right? And if you want those devices to do it evenly, then you have to allocate memory in this range. Actually, I probably should take it back because these days, there is a page table like data structure between the device and a physical memory. So if you have a device, instead of like having, I mean, the reason for that, I keep bringing it up once in a while. So can someone tell me the reason? We discussed it during the office hours. There is a page table here sitting. It's called IOMMU. IO memory management unit, right? So why do we need this page table? It's a different page table because this page table maps from device virtual addresses to physical. Yeah, because normal page table will map from virtual addresses to physical, right? So the CPU itself, like imagine CPU sits here. If you're using an address in register, move, let's say, something EAX, say RAX, then it will use this page table to go into physical. When device issues an address, it will go to this page table and maybe it will access the same physical address. So why is it needed?
The reason I'm familiar with is that sometimes the devices have their own DRAM And the IOMMU will track translations to the device's private memory or local memory. But it also does translations to physical memory. And in that case, it's just isolation, I guess.
Isolation is the answer I was looking for. I wasn't exactly sure what you were trying to say when you say, I mean, first of all, most devices will have some kind of memory, like most modern, like typically this memory is not even exposed, right? So it's internal to the device. So I don't think it matters, but isolation is a trick. And there was a famous attack, which is called evil maid attack, when someone shows up and just plugs a device into your machine, like a USB device, and machine may be suspended, but might be running. And then the device, this malicious device, without this page table, can access the entire memory and like essentially steal all the secrets, right? Evil made because it, you know, you left the room, someone plugs the device and just reads your memory, right? And so modern machines support this IOMMU, which sits between the device and the physical memory, and it actually explicitly maps the device and the addresses which device can access, right? And you, like, operating system control the mapping, right? And it can be contiguous here or like random, but whatever device sees it as maybe like as 4 contiguous virtual addresses, and which maybe mean that you don't need this technology anymore. Maybe this is rooted in the fact that this is pre-IOMMU era, where you say device really can only like before the IOMMU, you couldn't like configure this like the lowest 32 whatever 4 GBs of memory to be mapped anywhere, right? So maybe it's actually obsolete, but I didn't check it, right? So I don't know it. But essentially the idea is that you might be able to track some special regions, and that's why those zones which Linux introduces, it says, okay, there is like some special zone for these legacy devices, and they call it zone DMA, and then whatever other zones, and those are coming probably from here, like even from here, it's one NUMA node, essentially physical memory attached to, let's say, like here on the left, and if you have another node, like for example this one, then there will be a range of physical addresses attached to this NUMA node, right? And I mean, it's very important in terms of performance, because as I was saying, accessing remote memory takes at least like 100 something cycles longer. So you lose both latency, but also throughput, because this link is limited, right? So, and on modern machines, it's roughly speaking 120 gigabytes per second, GB per second, one way. It's bidirectional, so it's really 240. But if you like, for example, reading something, your read from that memory will be limited to 120 per second. And if you never seen this number before, like you don't even know what those links are, meaning what kind of exact capacity for those links. I'll ask quickly a question here. So someone tell me what's the bandwidth from a local port, for example, to local memory. And it varies, and there are like different things which define the bandwidth on this link, but I just wanted to make sure that we have at least some notion for this number. Yes, in the back. Say, guys in the back, you know, 240. So Jerry says 240. Jerry knows because he was working on it, and Josh knows. So it's like, I should probably come back with a couple of slides on how to calculate this. But really, particularly modern CPUs come with multiple memory controllers. Each memory controller has I think at this moment 2 memory channels. And those memory channels, when you buy memory, like DRAM, you probably see those numbers, something like 520 or 5200 mega transactions per second, right? So in the transaction, I think is 8 bytes or what, or 64. 16 bytes, maybe 16. And then from this number, you calculate the frequency, but there are different components on the CPU which limit you a little bit, so you don't have the theoretical maximum. Roughly speaking, it's 240 gigabytes per second. Just like again, it makes sense to remember those numbers or have some feeling about it, right? So meaning that when you run something on this course, ideally, if you build a real operating system, you try to allocate memory locally. It's not always the ideal strategy because sometimes you say, look, guys, even if I run a bunch of threads here, I actually want to utilize bandwidth of both on both sides, right? Which means that you might want to split it between like local and remote memory. And typically, operating systems will allow you to expose some interface like this will allow you to go to express the fact that you want to allocate memory here or there, but for lay user, you have to allocate typically local. So, Hong, you had a question?
This 240 gigabyte per second ballpark, is that for DDR or is it more specific for DDR?
This is for DDR5, which operates at this speed. I think DDR4 was something like, I would say 34 or whatever the number was, megatransactions per second, right? So like the previous generation. And that number was, let's say, like, good exactly, but like we can recalculate. I can come back to this. But this is for modern kind of like,
yeah,
but that's why like whatever the hyper whatever next memory. Okay, and now what sorry for this kind of detour, but what Soham asked, he asked, if I understand correctly, is it the case that those DMA zones should be per node or not? And the answer is no, because it's really, in the end, the way the memory controllers work, they map all available remote, local, from all the nodes in the system memory to a consecutive region of physical memory, right? And there will be just one set of those low memory addresses, right? And this is like the special zone which Linux tracks, which, as I keep saying, maybe it's no longer relevant with IOMMUs, but I don't know for real.
So with the IO, like in this traditional like layout which you described, we will see a higher traffic in processor 0 because it's kind of managing the memory for all of these things. But if the IOMMU is there, then we can assume that the memory allocator will even be right.
Wait. Like, yeah, so I mean, it's up to you, honestly. So I'm just my goal was to tell you the story. So for two reasons. First, that you know that this exists as a problem, meaning that if you have a device sitting here, DNA from this device will go faster to local memory compared to DNA to remote. So when you configure IOMMU, you probably want, I mean, depends on really, I mean, maybe in some exotic cases, you might have to split it in between the two. That's beyond what I wanted to discuss. But I mean, and the real case is that I'll give you an example just for the sake of example, so it doesn't hang in it with the hand. So imagine, just for the sake of example, imagine that this physical memory is roughly split in half, and half of it sits on a local node, and this device is attached to like CPU 0. And this one is attached, and this is a remote memory attached to CPU 1. You might want to split the allocation, saying that okay, part of it sits on memory, which is here on 0, and half of it sits somewhere here. But the reasons, if this device, and this is where I lack knowledge. So if PCIe has higher bandwidth, it's also like it's controlled by how many channels are there. And you somehow can say, look, I can easily saturate the bandwidth to one of the NUMA nodes. Then it makes sense to split so you can like saturate more.
I think I'm asking about a simpler example.
Yeah.
We assume the zones are as they are, how you describe it. And in that case, it's probably all on processor 0's memory.
Yeah,
like
most likely,
yeah.
This zone low, whatever, DMA,
yeah,
most likely will be attached to
processor
so 0.
for this PCI device attached to processor zero's PCI controller, makes sense that it will use local.
Unless
If,
it
but if
can
you-
saturate the, unless it can saturate this.
yeah, and then, but that's developers. But
Yeah.
if this device is connected to processor one's PCI controller,
It will have to go across.
so that all accesses would be remote access.
Yeah, correct, yeah.
That was my,
Yeah.
but
Well, that's-
I'm guessing the IOMMU would take care.
Yeah, so if you stick an IOMMU in front of it, then you can remap, make sure that those accesses are local. And there was a paper written by, I mean, I know some of the authors, but I think it was called Octopus or something like that, which was studied those FFs. It came out in ASPLOS a couple of, let's say, 5 years ago. And they were studying whether it really changes performance. And I think it's worth looking at it. So I don't know the answer myself, but it probably is. But we got the point. So like, essentially, it's a distributed system, and you might like 3 things will be at play. Pinning your execution threads to cores, making sure that they don't move here, for example. Allocating memory on local and remote nodes. In some extreme cases, also allocating IOMMU in such a manner that devices DMA to like local memory. By the way, there is also a funky technology which allows the device to perform the DMA not into memory, but in the last level cache of the CPU. I forget what it's called, but it exists. And in some cases also give you performance, meaning that you don't have to, you don't see cache missing, because if the DMA goes here, then you access this memory, you're using the cache and then you pay the price. On the other hand, if the device immediately DMAs into last level cache, or maybe even like higher caches, then the memory, the cache line, higher cache line is here, and then it's easier to access. Again, if the discussion gets complex because you can always prefetch and stuff like that, so a lot is at play, so it's not always trivial.
So what you were describing about the caches, that's also part of the coherence subsystem.
That's a good question. And I answered it.
In the gray solver architecture, that's what it was. So the IOMMU kind of maintained coherence with the GPU's cloud other cache and the CPU LLC. So
Which architecture?
this was, the CPU was ARM and the GPU was PTX. So in the ARM PTX model, the CPU L3 and the GPU L2 were cache, and the requests were direct.
Yeah, but Intel has, I think it's non-coherent on Intel, but I don't want to, I don't know.
I was just saying like in one case.
Yes. Okay, but this answers the question, right? Which, okay, cool. Sorry, it took us some. Okay, good. So this is where we were with memory allocation. And I said, okay, guys, so the tower of those allocators, which I was like describing all this, like the tower was, let me just draw it really quick. Like again, if someone pays you money or like interviews you trying to stress your understanding of what's going on, then you say something like, we have nodes which track NUMA memory, like we just discussed, local, remote, we potentially can have a list of those nodes, right? And then on top of each node, you'll probably build something like a body for large memory allocations, right? So the ones which are powers of 2, and the ones which we like will be splitting in half every time. And on top of body, we will build something like what is it called? Slab. And slabs will essentially allocate something from body, and we'll have a list of small objects which fit into, let's say, a page or 2 pages, let's say 2 pages, 4 kilobytes. And you also can have like use some external metadata, which seems to be like a better choice to track the slab list, right? And you will be having like partially full, empty slabs, empty, and full. And typically when you say box in Rust or something like malloc, in C and you say object is 47 bytes, then you say, you know, you will have a collection of those slabs of different sizes in powers of 2, but let's say up to maybe 4K. And then you land on the next power of 2, go into a slab, return an object, right? So you will get a pointer which points into the slab. When you run out of memory in a slab and you don't have empty slabs, then you go down to body and like allocate the size which the slab requests. In this example, it's 8 kilobyte. When the body runs out of memory, that's a good question, actually. I don't know what to do when the body runs out of memory, because typically you initialize the body with all available memory from the entire node. So supposedly everything was already on body at this point. You can come up with some fallback strategy to say, look, if this body has no memory, I will traverse this node list and ask another body for memory, but that might break your guarantees. So that deserves a discussion. So I don't know. Ali?
So then you're saying that if you run out of memory in your first Newman node, now you're gonna be non-local?
Yeah, no longer local. Yeah. So if you, I think this is behavior in Linux, but you can say, you as a designer of the system, you can fix this behavior and say, look, maybe I will say error, no, out of memory. Maybe it makes more sense to allocate remotely, but okay. You can also, I mean, when I was a student, I got unlucky. I had a machine which 2 processors had no local memory. It took me a while to understand that because I mean, I wasn't at that level. And then I suddenly realized, this guys, it was the fourth. These guys really suck. They're so slow. Like everything what I run comes so asymmetric and weird. It took me a while to figure out that they simply don't have local memory. So in this case, this kind of fallback strategy totally makes sense, right? And maybe it makes sense because it's all best effort, right? Unless you have some other interface which says, look, I want to allocate something, and you go probably directly to body with some kind of a flag like NUMA node 1 or NUMA node 0, and you go to this specific body, or maybe you say, look, why it matters? Because you like the stuff which we're working here in we typically like everything starts with one thread which runs on one of those CPUs, and then we allocate a ton of different memory, requesting memory from NUMA node explicitly from 0 and 1, for example. And because it's remote with respect to this thread, this some fraction of this memory. So the operating system will give you an interface where you can say, give it to me from NUMA node 0, and then it will go. It's kind of like flipped at this point, right? Because you say, you first navigate the nodes, figure out which one is 0 or 1, and then go to a body from this node, which means that probably drawing this upside down makes sense. But what I meant in this drawing is that all the memory for this body will come from this node.
Which of these allocators have a view of this? Will it just be the NUMA allocator? Because like it seems like
Well, like the way I think Linux does it, and again, you can do it differently, right? So I think each of these nodes will have this metadata list, right? So this will have a metadata array list, which kind of represents physical memory.
Right.
And then body sits on top of it, right? So this will have its own, and it starts maybe from like gigabyte 128 or something, the second node, right? And this is what tracks metadata we discussed before. So this is your exact knowledge of physical memory in this page array.
Right.
And then body has some knowledge about it. It knows that it will be allocating to this page array, but I don't think it knows that it's specifically node 1 or 0. So this level will know. So if you have a flag like NUMA, you have to kind of punch that, like whatever. Come to this level, from this level resolve into body, into a specific node specific body. And then from here you can pick memory and allocator.
So body directly returns virtual.
Yeah. Like I don't think, yeah.
So I'm confused about the relationship between NUMA nodes and buddy. Is it that a buddy will own an entire NUMA node, and then when exhausted, request a whole new one and also own that? And then if they deallocate everything in one of these nodes, they'll release the whole node.
I don't know. I don't know. I think I looked at it once. I don't remember anymore. That's a good question. So if you run out of memory in this body, there is a chance that you go and fall back to some return paths. And this return paths will go back to the node level and says, look, you ran out of memory here. So do you have a link to the next fallback node? You go here. This says yes. I redirect you to my own body. This one will look up and this returns from here. I don't think like one body can borrow memory from another. The interface, more logically, it will be easier to build when you drop. If you fall back, you drop out to the nodes level and go to a new body. So kind of like iterate through all available nodes and bodies until you figure out memory.
So it's one-to-one for NUMA node and buddy.
I think so.
And then if your buddy has no space, it asks another buddy.
I don't think body asks for space. If it ran out of space, I think it will just say, I'm out of space.
I don't mean it would grow itself, but I mean.
It will probably just return an error to the layer above and say, look, I don't have any memory. And then you will implement logic there, but I can build.
There's like one
Question. I think, that's a good question, and I don't know the answer immediately.
because like the body is magnetic.
I think in the end, this is a thin wrapper around body. You would have to maintain a list of bodies. Zones don't do much. The only track those funky, if I remember correctly, the only track those funky like DMA zone. Like for example, if this is the node, then it might have multiple zones, and a zone will have a specific flag. And then when you do pass a flag like DMA, it will try to figure out the matching thing. And maybe this is one-to-one. Maybe there will be like 3 bodies. It looks like it's per zone.
Per zone.
Right.
So
No, like I would build it per zone. So for example, I read all the available. I mean, let's forget about this normal zone DMA. Like we just say, look, we just will track NUMA. I will say, look, for each of the NUMA nodes, I will have a private body. And the reason for that, so I can implement local allocations later. And but in Linux, and that would be my nodes track NUMA nodes, right? And zones will track some funkier subset of memory, low memory. You probably don't want to mix them because you say, look, because body guards you with certain ability to allocate objects of different sizes, like 4K, 8K, 16K, and so on, right? Until some max size. If you want a larger, in the past, there was the problem that physical device driver says, okay, I really need 2 pages, continuous 2 pages, or I will not be able to work. If you don't have IOMMU, you really need to allocate continuous 2 pages. In order to track continuous 2 pages, you cannot like go and ask it from Slab or something. Body was this mechanism, even not linked list, because linked list, you have to fix the size, right? Body kind of fix a collection of sizes from 8 to, I don't know, let's say a couple of megabytes, right? Or even gigabytes. And so that's why logically body will be per zone, 1, 2, 3, and this is 1 node, then 4, 1 node, 5, on this one. So on this NUMA node, you might have like 3 bodies, zone DNA body, zone normal body, an N body. On this one, just 1 body. Okay. Makes sense. Then you have this flexibility. And then it's like that. And then if you access the, like if this guy running on C processor, let's say 1, says, okay, please allocate me memory from NUMA 0. So it immediately goes into this zone, into this node and a specific body on the node 0. And so you have to implement all the proper locking to make sure that accesses are serial, like properly synchronized, right? But that's probably not a big deal because you only rarely do those operations. Typically, your interface to allocator is box and malloc, right? So you just very efficiently allocate from those. Those by default will be local to you, and so you cannot pass an argument to malloc saying malloc me 47 byte object on a remote NUMA node. Why is that? It's just a bad design decision because this flexibility for the small objects doesn't make sense. Like typically, you will care about large regions of memory. You can, but then you're going to lose a lot on synchronization, right? And so typically you would have something like slabs are probably also local to specific NUMA node. But again, you can design it differently. But the idea is that even if you're requiring to lock somewhere on the slab here, this lock, in most cases, this cache line where the lock is stored. I'll just erase everything here. Will stay somewhere on this processor. So it's easier to scale if it doesn't migrate outside of it somewhere here, because this is where performance goes. It does drop when you have like 38 cores, 32 cores here. So ideally, you might even split the system again off, make sure this lock is accessed by a smaller number of processors. But I don't know, like, I mean, we never really discussed how locking and performance issues overlap. So I don't know if it's worth discussing right now or better coming. We should come back later. So now, did you understand all of it, right? Right. So then my kind of thing is that, okay, guys, most likely it's very hard to build. My buddy, this Gerd Zellweger, who, we'll take a look at his source code. He built it, of course, for his operating system in Rust. And he was the one on this Octopus paper as well, I think. But for us, it's too hard, right? So can we somehow build a simpler version of all of it just to get it going? Our end goal is to have, remember, we have this list of what is it we're allocating. So we want to have box, make sure that we can allocate regular heaps objects in Rust. And we also want to allocate something like 4 kilobyte or maybe 8 kilobyte, or maybe forget about it, like just 4 kilobyte and let's say 2 megabyte objects for user memory. Because when user says, okay, look, I mean, hold on, is it clear that user doesn't touch this allocator at all, the user code? Okay, if I ask you a question like, when the user code does malloc, like imagine it's your application, whatever, hello world, and you say malloc, or box if you like Rust. So where do you land in this hierarchy?
Higher than all of it.
Higher than all of it?
Well, I say that because
No. Eventually, you need to allocate memory, right? So you have to plug in.
Body, ask the body for memory, which asks the Slab for memory. If it doesn't have any space in the NUMA, then it asks another body, and it keeps looping until you find somebody that has.
Until you find somebody. You understand that when you say malloc here, there will be another tower, which is similar to this tower of allocators, living in user space. So this is ring 0. Typically, we don't draw rings horizontally, but I ran out of space. So this is ring 3. And you say malloc, and typical allocator is, you probably heard this word gmalloc or something, right? But you can think of like exactly the same thing. So kind of slabs running here. And I mean, people spend a ton of time on optimizing those allocators. and making them more secure by actually saying that they are less exploitable. They are hardly more secure, but they are less exploitable. Let's say I'll call J. What is it called? J.
Where did you get that word
Today I got it from the source code because Japan, my student, was coding against atmosphere. The user level uses a stock draft trait which implements JML.
Oh, that's just like an algorithm that's well known.
I think so, yeah.
Oh, okay.
But what you know something about it?
No, I think a professor from my undergrad has do an assignment called JMAC, but I think it's because his name started with the J.
Maybe, but
I
it's
think
no,
he
it's
did.
just like for real, there's a I mean, for user level, the performance trade-off is slightly different between those allocators. And so JMalloc might be, I don't exactly remember what JMalloc does, but like when we write those allocators for ourselves and we want to beat the performance of like stock allocators from like libc, we usually do something like log-free per core, yada yada. But at a simple at a high level, it's just the same. So you say, look, I want to allocate objects of some size, so I will be tracking array of different like slab-like data structures, which maintain those linked lists and stuff, right? And maybe still out here. And the idea here is that typically when you say, look, but I ran out of space, there's no space here. At this point, you say, look, I will use operating system interface on Linux, let's say it's mmap, right? You map additional memory and you can specify some size, let's say 8 kilobyte or 16 or whatnot. And this is a system call interface, right? At this point, this user level allocator doesn't have a body because it can rely on mmap, and it just mmap drops into the kernel and probably plugs somewhere in the body hierarchy because it already says 8 kilobytes. And so you say, look, I will allocate you 8 kilobytes from my body. And then if it fails, it goes down to a different NUMA node, allocates from that body, returns, right? And mmap, of course, patches your page table saying that a region of new available memory showed up. It's 8 kilobytes in your address space. And then you say, look, okay, sure, I will initialize more of this on top of this 8 kilobytes, right? Makes sense? So user level and user level JMalloc typically will only cover this thing, and it will have some kind of a fallback methods to say, like, give me more memory. And for the kernel, is give me more memory is body, right? So at user level, there will be no body typically, unless you're building something like a database system and you say, look, I'm so clever. The kernel mmap is so dumb, and what I want to do is I will allocate half of my memory from NUMA node 0 and NUMA node 1. Again, because you're so clever, it's your PhD. You say, look, I know that like I built the database engine and I have to access to this memory. I have to make sure that it's local, and I'll be tracking regions of this memory, and then you essentially re-implement the body on top of this, if you like. Typically, it's not the case, right? That makes sense? So now we understand how. Okay, cool. And typically you optimize for like log-free access to those guys because those allocations, I mean, the kernel is relatively long-lived. Those allocations are probably even higher frequency than whatever the kernel is allocating. Let me do it like a slide. Sorry. If I draw you this diagram, what's missing still? Like there is a funky performance case which you might choose to handle differently in a kernel. What can be this performance case? Speed, yeah, but like give me an example. Allocating what kind of object? Where? Big page, that's a good example. Not the one which I was thinking about, but that's a great example. Yeah, so this body on its own actually, I mean, maybe it's possible to merge it, but if you say, look, I really want super giant, I want to leverage 1 gigabyte pages, like huge pages. I think you still can rely on body, and you have to rely on body to track all available physical memory, because this will be the size, the biggest power of 2 sides of tracking. And you can pragmatically if you say, look, it doesn't make sense to allocate anything larger than 1 GB because just practically it just doesn't make sense. You can't even map it. So maybe body can exactly solve at 1 GB, and then you just plug into body and allocate from there. Plus, it will touch your page table to make sure that this is like you can like essentially. I didn't talk about it, but you also have for a process. If this is virtual memory of a process, you have to track which memory is available and which is already taken, because all these libraries which you're mapping, like all these shared libraries and stuff, will create holes, and some region may be reserved by the kernel. So you have to actually, when someone says nmap, Linux, for example, I don't think it allows you to pick an address, honestly. It will go to a special data structure in the Linux kernel, which tracks availability of those empty regions, and we'll pick one and put it here, right? So that's fine. But imagine the kernel itself, like I mentioned, the way I got to this question, I said, okay, user level allocations are so frequent that you might replace this slab scheme, which I had, let me show you, which I had here on my slides, like something like this, with something even more faster, and this faster is malloc, jmalloc, for example, for user level. But will you ever arrive into a same case in the kernel where you say allocations are so fast that even the overhead of those slabs is higher than I want to tolerate? So what would be this case? What's the, yeah, so
I can only think of like if you're allocating a large number of really small objects.
correct, and what these objects, and not once, but constantly, over and over and over. So the real question you have to answer here, what is this physical event or event in a kernel which is the most frequent and requires allocations? Context switches are relatively, I mean, I forgot who was that, or maybe it wasn't this class, but someone had a funky plot which was mapping those numbers to real years, and it's almost like it's a million years. And if you map, if you say that 1 nanosecond is your day, then of course the proportion will be, it's a ton of time. It's 20 million cycles, right? It's very, very rare, because the pass through this allocator is roughly, okay, well, who can I involve me? If I say box in the kernel, and we assume this power of allocators, a typical average allocation of like 47 bytes, how long it will take in terms of cycles? That's a good skill, especially if you build compilers or anything where you start thinking about performance, or even when someone pays you money to make something fast.
Because under 200.
Yeah, so that's reasonable, because you say, look, like I go into this array, resolve one of these pointers. If I'm lucky, I'm immediately landing on an empty available thingy, maybe update some metadata. So if you're very, very clever, you probably can do it in like 20, 50 cycles, but maybe if there's a lot of metadata, you can go to 150 or something, right? I don't know the number, but that's the data structure doesn't require any walks. Like occasionally you like allocate from body, and then it's of course an outlier. It's bad for real time. If you like steering the wheel, then something can happen, but typically it's okay, right? But what is this event which happens like even more frequently, or on the scale of 20 to 150 cycles? Oh yeah.
Are you? I'm answering the previous question. I think it's file descriptors.
File descriptors. Do you open that many files? Maybe. No, it's a reasonable. It's a step up from context switch, right? So obviously, you will probably imagine you like I don't know what it will be, but file kind of serving service where a new incoming internet connection, and you immediately open a file descriptor and send it out or something like from Apache or something. That's closer, but still probably it's like thousands or tens of thousands of cycles. So probably this allocator will be just fine. So
And the last remaining thing is network packets.
Correct. Network packets. And / NVMe. But NVMe is typically larger because those go in units of 4 kilobyte. And network packets can go up to like 64 bytes, like whatever. The minimum packets is what, 48 or something, I forgot exactly. Or 1 kilobyte. So those two, when someone tells you like, what is the most like frequent event, it's not like a timer interrupt, because the timer interrupt you typically configure to arrive once in 10 nanoseconds, which is 20 million cycles. But the network packets, even on like 10 Gbps interfaces, which I was mentioning before, I think 1 kilobyte packets to saturate 10 Gbps device link with 1 kilobyte packets, you will have to send out a packet at roughly 860 nanoseconds or something like that, right? So which is like 160 cycles on a 2 gigahertz server, right? So, but smaller packets or on the devices which are 100 Gbps, right? So divided by 10, it's 160 cycles, and you cannot tolerate the latency of 150 cycles of allocating a packet. Okay, that's good job. Like we figured out those are the network packets, possibly NVMe. I mean, I actually don't know anything about GPU devices. Maybe they do something similar. So that I take it back. I don't know. But anyway, so how to optimize this allocator for this? Can we make it even faster? Can we drop this to like some number, 5 cycles instead of 20, 150? So
Like I can just think of like if you know your network packets are going to be a constant size, then allocated slab.
Correct. And that's exactly how it's done. So Linux also, and it's FreeBSD as well. Linux, I think, I forgot the names. Oh yeah, but I forgot actually the name of Linux. But the idea is the same. That it says, okay, kind of allocate one giant slab of objects of the same size, and say network packets. And if you do like there is a memory stats on Linux, it will show you that those slabs exist. The reason I know, because when you debug sometimes and you say, look, what is leaking memory? You look at those slabs and you see, oh man, I forgot to deallocate a packet from this slab, right? And so it's of objects of one type, meaning one type and one size, like network packet. And then you say, look, it actually can go and you can drop performance because you're bypassing this. But then instead of box, you really use this. I mean, I don't know what the interface will be in Rust, but you say box or packet box, key box or something, and you allocate from here. In C, you would just say like whatever, slab alloc or something, and then it will go directly there.
So then is it the driver's responsibility to create the slab? Or
Yeah.
Okay. So,
Or the network stack, typically the network stack.
but there's no like auto detection.
No.
I'm seeing a lot of 172 byte.
Yeah, so maybe someone who does ML, would say, look, we'll do this optimization in the kernel. But kernel developers, yeah, everything is hard coded. But that's a decent idea. Like it's important to understand that if you want to achieve this 2.5 cycles, then you really have to bypass this generality and trade it for it's less general, more but faster, right? Okay, cool. So we got this. Any questions? But I wanted to come back to this. My question. Okay, this is too complicated. Gert can build it. Gert is from what is it? Switzerland, ETH, no, EPFL, something. The best school in Europe, maybe. But we probably cannot, right? Especially after the homework is due after the full break, homework number 3. So how to simplify? What's the minimum allocator we can build so it satisfies our purposes, but can be built in a couple of days of work? That's the goal for the homework.
Slab seems like the easiest.
Slab, but slab doesn't exist without body, because slab has to feed.
We can change.
Yeah. So how will we change this?
Like if slab, like currently one side of slab is the user and the other side is body. If slab directly works with physical memory.
But someone has to track available physical memory. How will you do it?
Like
I mean, I'm not saying it's impossible, but what I'm saying.
Like I'm just thinking the free page list, the page
Array.
Yeah, that directly plugs into the slab instead of body. So we'll obviously sacrifice some performance for larger allocations. We can have a page-sized slab. And
maybe reasonable, but then you sacrifice the ability to allocate 2 MB pages. And it's fine. So as I was saying before, you can probably build a kernel which uses only 4 KB pages, but I just wanted, for the purposes of illustrating this example, but also to support 2 MB pages for the user.
so
Although you can
4 KB slab and 2 MB.
a 4 MB slab and a 2 MB slab. Okay.
And smaller slabs.
I kind of agree. So, but is that the one design choice which we all want to go for? I mean, of course, I will push you to a specific design choice, but let's have an illusion of freedom. I mean, but we'll have to fix something. And I'm not saying like build whatever you want in your homework, just, but something reasonable I have to suggest.
Well, I think you could take out slabs and just use buddy and have smaller powers of 2 also available. So then you're directly taking a whole chunk from buddy instead of subdividing it further.
Yeah, and that was my actually idea as well. So I would say even building slab is a little complicated. There's like logic of partially filled something. If we just build a very simple body, which can allocate only 2 sizes, 4 KB and 2 MB, it will probably sufficient. I mean, it's good enough to illustrate the point. Let's build an allocator. Everyone plugs it, like works on it in Rust. Everyone feels the pain of like using the pointer or something, right? But at the same time, it's not like killing you and crushing you. So, and if you know the whole story, then you say, look, okay, I built body and I have nothing to do on the fall break and I will build something else as well. But probably this idea of going with a body which uses just 2 sizes, 4 KB and 2 MB, is probably just a meaningful way of going.
But in this, we're also working on the merging splitting.
Yeah, but I will suggest them in a second, but they are like very, very simple.
Right, so just 4 KB merge.
Yes, and nothing else here. If you can't merge, oh, you're unlucky. I mean, I'm pretty sure that this system is not ideal.
Like in my head, the only difference I see between slab and body are
I agree with this.
the full partial free.
I agree. Yeah. And I mean, feel free to build something, but my goal is to assign something what doesn't crush, your soul, and like just, just dumb word. And at the same time gives you a flavor, and it's not completely dumb as a like bump allocator, which I mean, Philip talks about sometimes, or you just have a region of memory and you have a pointer and you say, look, next allocation pointer advances. And you never deallocate, you just move one way. So which is also a practical choice when you're booting a system and you say that this object will never be deallocated. So it's totally fine to do this, but it's a little odd, kind of like teaching a grading system class, which only uses this allocator. So any questions?
Now, I don't know much about the details of how Rust memory works.
Yeah. Hold on, let me ask a question first about Rust, and then probably I will answer just because. But I can answer too.
So what I'm wondering is like with the Linux kernel, we have so much magic with the slab and the body because C is dangerous with memory, but
No.
can we leverage Rust's memory practices to avoid something?
Yeah, and this is what I also wanted to answer, that there is no significant difference between the act of allocation in Rust and C. It's the same. Rust doesn't give you any edge of this. The only thing is that Rust implements automatic memory management, right? It tracks memory statically and in a drop method over when object goes out of scope. And I'm kind of lousy here, so I don't even remember exactly how drop works in Rust and everything. It just inserts, like the drop itself has a free, right? And so, and here you have to do it manually. And if you did it correctly here, then fine, you're lucky, there is no bugs. In Rust protects you against this, unless you did something like unsafe here, and you made a mistake and your unsafe is not exposing a safe interface, and then this free results like in another access later, right? Which is also very, very the reason I bring it up, it's not because I want to be again esoteric about anything, but in a kernel code, unsafe will be your, like, roughly speaking, not the best friend, but you will have to deal a lot. It's not my like personal observation. People who try to bring Rust into the Linux kernel, well, they carefully spell out what is safe, what is unsafe, and it's not easy often. Like there is an informal argument here where a person writes that I believe that this is unsafe because X, Y, and Z holds, those invariants hold, and that's why it's safe. I mean, I wanted to say safe. Got it? But that's essentially one-to-one. Rust is so thin, if you think about it. All of this box and drop business, it exists only at statically at compile time. You run like a sophisticated borrow checker, which reasons whether all the like lifetimes are there. You like don't leak the references outside of the scope or something like that, right? And in C, but underneath it's exactly the same.
Nice.
So there is, but I wanted to make sure that it's also clear, right? Okay, so we got this. Okay, so but what was the question? Sorry, you were asking. Can
That
you
was the
leverage?
question, can you leverage Rust features, but you're saying it's just a wraparound.
Kind of, yeah, in my view. But again, like language people might disagree with.
I think at like there's two layers here. This is the user side. But there's also the implementing the allocator
Mhm.
side, which we'll be doing.
Uh-huh.
And I think on that side you get universities in addition from Rust
Mhm.
and C does.
Mhm.
I think the only thing would be the APIs for writing allocator. Let's make it a little nicer.
Right. Yeah. No, you're right. You're totally right. And we have to come back to it. But essentially, in Rust, it's very easy to say, oh, by the way, that I think you can only like global allocator or something, global alloc. I forget exactly the attribute, but essentially it says, okay, this will be my allocator for this code. And in C, it would be probably you have to do it at the level of linking or something to define those malloc and free, but let's not go into this, right? But more or less, Rust is very well thought about, like actually to some degree, because there was some argument that allocator interface in Rust was too restrictive. But wait, hold on, let's build it because there is not much time left, 15 minutes. So I suggest to build it as we're coming back to this page array. Essentially, remember we said, okay, we're going to allocate it dynamically, pass the end symbol of the kernel. We're going to grab the size of this array. There is an interface provided by, actually, first, we're going to grab from the grab, a different grab. Grab exposes you a data structure, which is called info. And as part of this data structure, there will be a memory layout, which grab picks up from bias. And this is kind of hard, and let's not do it. But picking up this info, we know the max size of it. There might be holes, and we say, like, let's just go with the maximum address. And even if there's part of it is not used due to the hole, that will help us to track what's empty. And then each element of this page array will track some metadata about the page, right? And we allocated it dynamically, so we can support any info. Unless someone, yeah, I think array is always smaller than physical memory. And we can implement it as, like we say, look, it will be a very diminished version of body. We're first going to skip 2 megabytes and say, look, this page, which is 2 megabyte aligned, I mean, maybe we'll like some of those pages are already taken, and we say, look, those are taken because the kernel is sitting there. Something, right? Maybe the end falls into this page. And then we maybe round up to the next 2 megabytes. Rounding up will help us to, this is a 2 megabyte alignment. And we say that this is a 2 megabyte page. And the next 2 megabyte page is this one. And this one is also has a type right now, 2 megabyte page, right? And everything is initially just 2 megabyte pages up until maybe like the last couple of pages, which we say like 4K at the very end. And then when we start allocating, we might have just 2 lists in body, like 4 kilobyte pages and 2 MB pages. And if a 4 kilobyte page doesn't exist, we go to the list below and split. So essentially, like just mark those like remove it from the 2 megabyte list, mark it as the 4K pages, all of this, and add those to the list, right? To the list of 4 kilobyte pages. And then we have like a bunch of 4 kilobyte pages. And the act of merging essentially, and you can think of how to build it smartly, but I don't even insist on anything smart. And to be honest, I don't even know the smart way to build it. But let's just assume that like this was our like 2 megabyte pages, and this is our like now 4 kilobyte pages. The merging is every time you, for example, deallocate a page. If it falls in the middle of this array, you just say, wow, it's still a 4 kilobyte page, but we mark it as free, for example, and you add it to the free list. But for example, at this point, you say, by the way, shall I try to merge? And you can do it like you can do a guess or try to merge every time. You round it up to your leader. I mean, alternatively, instead of rounding up, you have a pointer or like offset or something. And then you say, are you free? Well, yes, I'm free. And then you scan all of those pages. And if all of them are 4 kilobyte pages, which are free, then you can merge it back and say this is actually, now it's part of a 2 megabyte page, right? Locking and synchronization is a little bit tricky. So you have to acquire a lock on this guy. And then all of the guys as you merge, right? And if you want to merge, we can like just realistically, just to make the homework simple. And I would rather say, let's build, because the plan is to late, let's build allocator. We have to build a page table. It's homework 3. We still have homework 2, which is like pending, it has to be assigned. But up to that, we want to use like, want to use user space and build a context switch. And in order to fit those, I would simplify allocator as much as possible. So I would say, don't even merge. Just split is enough. Just to make sure that you can allocate. And your box will be built on top of this interface. And you say, look, 47 byte object. Well, unlucky, you have to allocate the whole page, but that's fine for us. So yeah, so I'm done. So I mean, I think this is what I suggest. It's slightly more sophisticated than a bump. It's reasonably practical because you say, look, but like if like again, there are those people in the community who will hold you accountable for any design decisions. And like people who build, like, for example, a CO4, they will strongly disagree with this simplification. And they will tell you, no, guys, like real systems cannot build this way. I kind of agree, but still, like if you really want something very, very fast, how many processes, as I was arguing the other day, how many processes will we be allocating? Oh, maybe 1,000. How many threads? Wow, maybe, I mean, I don't know, 100 each. So what is it? Another couple of zeros here, right? So if you like that's your multiplied by 4 kilobyte, okay, hold on, yeah, so you wasted like waste some memory, right? For real, but it's not again, maybe numbers are over exaggerated for us. We will be in hundreds, 100 processes. What hundreds? We'll be in tens and tens threads. Nothing, 4 megabytes. I scale you down. But this, I mean, it's not ideal, but you know how to improve on it. But you can start. If someone says, okay, give me an allocator tomorrow, you will do this and it will be okay. Make sense? Okay, so this is what I suggest to build in a homework. So I just have to write it, but I have to write the first homework first, right? So what about NUMA? Well, again, maybe as an extra credit, each NUMA node will have it's a pointer to a page array. So you have to think of how to allocate those page arrays dynamically for each NUMA node. I don't think even this info exposes enough information about NUMA, which is probably beyond what multi-boot header, multi-boot version 2 header does. I should check, don't know. So probably NUMA is out of the question. What about synchronization and locking? So where do we want to synchronize? What's the simplest answer? Of course, we want to access everything from multiple threads. Right? The kernel will run multiple threads as well, because we will boot multiple CPUs. Where do we synchronize?
So there's gonna be a head pointer for 4 KB list and 2 MB list. I guess first we acquire a lock on the head pointer. And then traverse the list. Once we find a candidate page in the list.
No, you land immediately on a candidate because it's a list of free.
Okay, right, so the moment we get the candidate, we acquire a lock on the candidate, release the lock on the head. And then complete the allocation. And only when we're merging or splitting will we retain the lock on the head, while also acquiring multiple locks on the.
I probably agree. I mean, maybe it's even simpler to just have one lock and don't even acquire a second because it will. But yeah, or if you're clever enough, and I'm not pushing you to be that clever, if it's a single linked list, you can probably make this operation as a compare and swap, which just flips the pointer. Honestly, it will not gain you much in terms of performance because everyone in the system, every thread in the system tries to do compare and swap on this cache line. It's kind of the same performance, maybe 2x faster, but really if you already lost you really will lose 500x on this. So it doesn't make that much sense, honestly. But
if we acquire locks on individual pages, then releasing the lock on the head pointer allows the concurrent allocation to take place.
Yeah, but yeah, I think you're not gaining, honestly, not gaining much. The only way to outgame this setup is to make sure that you cannot, because you always have to go through the head, and head is constantly updated. So it's invalidates this cache line from all other CPUs, because any write into this cache line will invalidate all the readers. So if you try to access it here, you have to send a request for at least for a status state.
Right, yeah.
So and this is where the bottleneck will be. Well, to some degree, but also, so really, the way to improve, and we should probably read the paper about it, is to have those heads, essentially have some intermediate layer of those sublists, which are per core. And then local allocations go into those individual lists, and never it will have a private head. And only when you run out of memory within this list, and it can be all over the place here because we don't care, but when you run out of cached objects on the list, you say, look, get me it. Then you go to this list and get a chunk of those objects and put them here.
Yeah.
So that's, and maybe actually this is the scheme which is used in those allocators like JMallocs. Essentially, if you didn't get what I was trying to say, just quickly draw it. And again, it's useful because, again, in practice, you will have to do it. So not in this class. So, but this is a reasonably practical scheme, honestly, which is actually quite kind of surprising. So the scheme which I'm advocating for is that there is a global list of objects. And two different head pointers in case of two CPUs. And those head pointers will have a stash of objects, each head pointer 1 and head pointer 2. And in case at some point you will run out of objects on this head. What's your operation? What do you do?
But the moment that happens, it goes back to the
Head 0.
classic case.
Yeah, but classic case, you don't want to take just one object from a classic case.
Right.
You really want to maintain a list of lists here, which have some number of objects here in between. And what you do is that you say, look, I will replace this pointer with this pointer, and all of these objects go here, right? And this can actually be done without even acquiring the locks, because this is a one pointer and update can be done with compare and swap. And then the whole chunk, if you fail compare and swap, then sure, this will be pointing here. And then all of these objects are elevated and go on this list, and then this guy will be allocating them locally and deallocating them locally. And then you have to implement the logic that when this thing grows too much, you do the same over this chunk. And this is a very practical scheme. Like we used it in practice. It's very fast. Like I was saying that when we wanted to outgame like libc allocators, we actually use this scheme. And this scheme is rooted in some published literature, but I don't exactly remember the, like, for me, I don't know if you're, this scheme, the person who introduced me to this scheme is Gary. Gary, I unfortunately forget his last name. It's the person who works for Flux for many years. Maybe you interacted with him. So when you allocate a node in Cloud Lab, so we had I challenged him to build a fast, slow-free allocator, and he goes, "Look, here I go!" Like, and he built it, and that's like fits on one page because it's all thread local data structures, and this is like one compare and swap, and it's kind of elegant, it's very fast. So what's fast about it that you never touch this head cache line, so it sits here, but only once in a while you come and update it, like, and it's almost there is no performance impact. And if you especially prefetch it to your local, you say, look, I have like only 2 objects left on my queue. Let's prefetch this cache line, and you quickly access it.
I'm thinking for our case, H1 and H2 could be pointers to 4 kilobyte pages. H0 could be pointers to 2 megabyte pages. And since we're already building the body algorithms, when H1 or H2 run out of 4 kilobytes, they can get a 2 megabyte split.
Well, I think merging will still require some logic. I don't see how you can merge.
But when
So-
it becomes you have a plus case.
I mean, maybe there's a way to build what you built. I would say that both of these are 4KB. This is the most frequently allocated thing in our system. And it's both 4KB. When this guy runs out of space, it just goes once and says, "If you give me one or a couple of 2MB," and here you apply a lot. But it's so infrequent. And if you want to allocate from this thread, you want to allocate a 2MB, okay, sure, suffer performance of a log. But unless you show me a use case where it's frequent, then it may be not worth it. But probably you can come up with a frequent use case. And then you say, look, guys, okay, I don't know how to merge log-free, so I will maintain both local versions of 4K, 2MB, and a global version of 4K and 2MB. And I will merge by acquiring the logs. But maybe there are some edge conditions where then this split becomes less possible if you're merging underneath, but maybe it's possible because you will be splitting something in the background and adding it to the very end beginning of this. So maybe it's all doable. But okay, cool. So what I wanted to say is this is what we want to build as homework. I'll write it down with a reasonable level of details. I would say this might be an extra credit for the homework making, and explain how to build this scheme as well. This is kind of practical and elegant scheme despite its simplicity. It's practical because it can be built in a page of code or in one page of source code. And what it means that imagine you're working on a new device driver in a kernel, and you say, look, I have to allocate packets very fast. And I'm building a multi-threaded program. So it's like allocations do happen multiple cores. I see like recess or performance degradation on regression, right? So when I like using a stock malloc, and I see the performance degradation when I use obviously my streamlined malloc, which was using quantum cache, right? But you can say, look, but I'm so smart, I will just quickly plug my own allocator, which does this trick, and then this performance bottleneck goes away. So we did it multiple times, it works for us. So it's a very practical scheme. Okay, so okay, we still have 4 minutes. Sorry, guys. 4 minutes, right? 20. Okay, so one last thing, and then we don't have to come back to allocators again. And it's reasonably boilerplate and everything. So that's why it doesn't probably make sense to like spend a lot of time on it. But maybe just like, okay, forget about it. What I wanted to explain the role of this global allocator, essentially what Talia said, how you build your own allocator, it kind of lives outside of Rust. Most of the code is actually unsafe. Well, I mean, you can write it safe, but then good luck to you writing linked list in a safe Rust. It's possible, but it's doable. But this compare and swap is Is what? It's unsafe, or is it safe? No, I think it's unsafe. Atomics are not safe. Or how? Like, because you need to convince yourself that this card gives you exactly one object from a list and not two, and the reference is unique. I'm pretty sure that you cannot do it in a safe Rust, right? But essentially, how we connect this allocator to box, it's a couple of lines of code, not super hard. I will refer to Philip's blog, and then the connection to drop, which is also not hard, mechanical. I'll give you a piece of code which does it, or close to a piece of code which does it, right? Then it will fly. Okay, good. So let me stop here. So then office hours are tomorrow, and I will work very, very hard to push that homework tonight. Like today, like for real, we'll try it. And then we'll see you on Wednesday.